So we're going to talk, so we're specifically from the London Underground part of TfL, and we're going to talk a bit about quite a sort of change of tack from the last presentation about actually how we can potentially improve the performance of our assets at London Underground. So by asset, what we mean is the actual trains, the signalling systems, the track, etc. How we can maybe, hopefully improve that through using data science techniques. So at London Underground, we're striving to provide, obviously, the best possible service to our customers at the lowest possible cost, and this cost thing is becoming more and more of an important issue across TfL. And obviously, the quality of the service we provide, there's a lot of customer experience and other things come into this, but obviously, what most customers care about is whether the tube train they're getting on in the morning is absolutely rammed or delayed or whatever. So it's obviously strongly dependent on the performance of our service delivery assets. So the trains, as I said, the signalling systems, and also other things like lifts and escalators, etc., that you find at the stations. All of this is sort of within our remit. And I mean, this is a fairly new endeavour at London Underground. So across TfL, data sciences has been used for a while, for example, to analyse Oyster card data and plan projects, etc. But in terms of actually using data science to improve asset performance, this is something that's quite a new thing. We joined London Underground about a year ago, and our remit is to leverage the large wealth of data that London Underground holds on its assets, along with external data sets where possible, to deliver asset performance improvement and ideally cost savings. So this next slide is supposed to give you a bit of a overview of what we're trying to do and the data sets we have available. So each of these boxes is a data set that we have potentially available. So right at the bottom here, you have the delays incurred. So we have we have information on what delays have happened, what caused those delays, what kind of an impact they had on the customer in terms of several X minutes. X thousand people were delayed for Y minutes, for example. And then we have information on asset failures. So when, where, how, why a failure occurred. Asset availability, so where are our assets? Are our assets available for service? Are trains sitting in depots? Are they out on the track in service? And so on. And then we have a wealth of other information, data sets that we can use. So information on how the assets are maintained, how they're used. So for example, the mileage that trains are doing, the condition of the trains. So for example, we've got some remote condition monitoring data sets which give you a feed from, for example, some of the train or signalling system, a live feed of the sort of life events that system is going through. So, for example, doors are opening, doors are closing, I'm going at this speed, I've suffered this alert, etc. And then we've got information on customer actions and external data set example would be weather, for example. So what we're trying to do, I've split these data sets into two. I mean, what we're trying to do is obviously, what we're trying to improve is related to the blue boxes. So we're trying to reduce asset failures, we're trying to increase asset availability, we're trying to reduce delays incurred to the customer. And we're trying, I suppose that the data science comes in, is we're trying to understand which of these factors and influence those things, the green boxes, and how do they influence them. Because if we can understand that, we can potentially make recommendations to the business about, well, we'll give some examples, but maybe you want to change your maintenance regime and you'll see an improvement in your asset performance. So we're going to basically give, the rest of the talk will be a couple of examples of where we've tried to sort of correlate some of these factors with some of the things we're trying to improve. So the first one will be looking at how our failure is basically driven by usage. So the number, is the number of operations an asset has been through, is that important for determining how likely it is to fail? So this is I'll show you sort of an example of where we've done this on the signalling system. This is sort of the data exploration side of this thing we're trying to investigate. We're looking at the pattern of signal failures here versus location. So this is just a histogram which shows you the number of failures on the y-axis, and then on the x-axis you've got basically a signal asset. It's not really important what it is. It's a sort of piece of signalling kit basically that you have spread across a whole London Underground line. And so this is just showing you the number of failures of those assets when you go from west to east across the line, the number of failures you're observing. So you can see that so it's looking at the pattern of failures by location, the failure rate. And you can see in this red highlighted box here, you can see that you can clearly see by eye that you've got a higher rate of failures in central London. So you might, what is driving that? These assets are identical across this whole plot. There's, as far as we know, they're all maintained equivalently. They're all the equivalent asset, equivalent age, etc. So something is driving that feature of their performance, that in central London you're seeing a higher failure rate. And so one hypothesis we had was that maybe it's to do with how often the asset is being used. If you think about how the networks, the typical London Underground line networks work, you can imagine you're going to get a greater frequency of trains basically in the centre than you are on the outside, a greater flux of trains through the centre. And this is what this shows. It shows you the trains per week for each of these different assets. So you can see these assets are called track circuits, and you can see that there's a certain category of assets where you're seeing a much higher usage of the asset, a much higher trains per week volume of the asset than other ones. So this higher usage occurs in central London. So it seems reasonable that this could be a factor that is driving failure. So to look at this in a bit more detail, here we've basically combined the failures and usage data and done a logistic regression fit to model the probability of failure as a function of the asset usage. So you've got three different. So along the x-axis you've got trains per week, so the usage of the asset. On the y-axis you've got the probability of at least one failure of that asset in a year. So you can see clearly that there's a relationship between the usage and the probability of failure. But furthermore, what you can see is what we've done here is split this data set that we've used to train the model into three different time periods. So you've got a very early period, which is the lightest green. Sorry, they're not particularly distinguishable. Then you've got a slightly darker green, which is the next time period, 2009 to 2012, and then you've got the 2012 to 2015. So you can see the lightest green, you've got some relationship. It's probably barely statistically significant, to be honest. You're not seeing such a strong relationship between usage and failure. But when you get to the later time periods, so as these assets are aging and wearing out, you're seeing this relationship become much stronger. And you're also seeing a shift, an overall shift in the failure rate as well. So this is evidence, we believe, that these assets are wearing out. As time goes on, you're getting more and more chance of them failing, and they're wearing out quicker with higher usage. So, as I said, these signal assets are basically identical. They're maintained more or less uniformly. So this potentially shows some potential for a risk-based maintenance approach. So you say my asset, which is my assets in the centre of London, these require more care and attention, and potentially more frequent careful maintenance regime than those on the outside. So this could potentially save you money, of course, because if you're at the moment we're maintaining everything in a careful way. Maybe you don't actually need to maintain everything in a careful way. You just need to target your maintenance towards these central assets, and you'll not only save money, you'll probably reduce failures as well. It could also indicate that potentially you want to overhaul these central assets and replace them. Okay, so now Emma's going to take over and take you through another example.
Okay, so Ben's just talked about sort of making some risk-based maintenance going on usage. So we're mainly looking at sort of how we can change how we maintain trains and prevent failures happening. So what I've been looking at is using some of the asset condition data. So what Ben mentioned was the train remote monitoring systems, where they tell you what sort of thing is going on inside them. Some of them more sophisticated than others. And I'm here going to look at one of the older systems, so it's not as sophisticated as some of the other ones that have got more data. So using these train event logs, and what I'm going to be able to do, hopefully, is predict how these use these to predict when failures are going to occur. And we looked at this for one particular type of failure. So what's train download data? It's just a time log of events that have occurred on the train. So this is what it looks like for a small section of the day, and you can see there's sort of lots of events that happen all the time, and some of them aren't that interesting, like under 5 kilometers per hour, over, under, over. Some of it's not that interesting. But there's quite a lot of events per day, so you wouldn't want to do this as a human being. It'd be quite boring. And also a computer can do a much better job at choosing things. So how we use this data. So I've looked at correlating events in the train log data with data that we get from the engineers about train faults. So the engineers write down logs about when failures have occurred and what they're due to. And then if I can correlate historically when the events happened on the train and when those faults happened, then we should be able to get an idea about whether the train is telling us that a fault is going to occur soon, quickly get me in to maintain me before I fail out on the track and cause a delay. So here we've got the train download data and the fault information for engineers, and then we correlate those two, then use that to create an algorithm. That algorithm flags up possible faults to engineers using a dashboard, and then the maintenance is scheduled so the fault never happens in the first place. So they're going to schedule that. So what we've looked at so far, so it's simplified first case, and it's looking at quite a large failure mode that we have on the underground. And you can, so we looked at just a single type of event and a single type of fault. So it's quite a very simplified way of looking at it, first of all. So here you can see that we've got a graph here, and it says Datasets giving, that's just the maintenance task that happens. And if you look at the red line there, that's when the event turns up in the train download data. So that's when it flags up something, is what that red line. And then if you see the sort of greeny blue line, that's when it has the fault. So you can see that the event turns up just a few days before the fault turns up. So that should be an ideal indicator for this fault, being able to fit this fault. So it's showing really promising results, and we're doing some further work on it at the moment. So one thing I wanted to put across was the fact that something that the business hadn't really thought about very much, which was about false positives. So it's all very well coming up with these algorithms and saying, oh yeah, well this indicates this, but some events turn up even on healthy trains all the time. So false positives are wasted effort. You spend a lot of time maintaining things that never would have failed in the first place. So ideally you want as few false positives, and preferably as well as few false negatives, so nothing to fail out on the track. So what I've got here is units with the fault and then units with the event. So these are your true positives, and we get 2.3. So these are the things that would have failed but also have the event, so that's good. And then the green one there is also good because these are our healthy units. They don't have the event, and they also didn't have the fault. The ones on the top right, they're the units that said, I'm going to fail soon, but never failed. So there are false positives. And our false negatives down here are the units that never had the event, but did fail out on track. So they never told us they were going to fail. So basically it was a way of sort of minimizing these red ones and keeping the green ones nice and large. So what are the expected benefits? This first simplified case that we looked at should reduce that failure mode by about 1/3. Should save the business about £2 million a year, including materials, labour, and a measure that we call LCH, which is lost customer hours. So it's our measure of delay, and it's how the mayor sets our target every year, or every 5 years normally. So he'll do it soon, hopefully. Yeah, it's clear that this data, so the data we've got could create huge cost savings. Yeah, I mean, this is just one failure mode. We could apply it to lots of other ones, and this is just one line. So it's currently being implemented with engineering, and they have a dashboard of alerts, and then it says it will look back in 6 months, but it's been going for about 4 or 5 months now, so it will be soon that we'll look back at it. And I've looked back at it on a 3-month basis, and it is working. It's just that we need more of an uptake with maintenance. So the next steps to train download data are using a larger number of events to help hone these indicators and improve their accuracy. We also want to look at a larger number of faults and hopefully prevent these and reduce our costs even further. And we currently have train download data. We do have more lines now, but we haven't worked on it. For one line, there are 11 underground lines in total, soon to be 12 with Crossrail. And the other lines, there are several other lines that actually have this data. So hopefully we'll be able to apply it to lots of lines, create lots of savings. So just to summarise what me and Ben have talked about. So in London Underground, there is a huge amount of data, and there's also a lot of external data that we can possibly use. And hopefully we can use it to improve the performance and understand it ultimately. So by correlating our faults that we've got from our engineers, the information there, with other information that we've got, it should be able to inform risk-based maintenance and overhauls, so massive projects that go on, cost lots of money, and then also predict when failures are most likely to occur and implement some preventative action, so when to do our maintenance. We've only just started tapping the potential of London Underground data to improve asset performance, so hopefully we've got a lot more to go, and that's it.